Alright, in this video we're going to do questions 63 to 65 of the June 2013 Chemistry Regents exam. Okay, so we got a couple of organic compounds here. It says these are isomers of C6H14. So if we're looking at this, it asks us first, what is the homologous series to which these isomers belong? So we can just look in here at our reference tables and see we have the alkanes, the alkenes, and the alkynes. So the easiest way to do this is just look at the formula, the structural formula of the compound, and see, does it have any double bonds or triple bonds? So if we look in here, we have all single bonds. And if it's all single bonds, that tells us that it's going to be an alkane. Remember, alkanes have single bonds, alkenes have at least one double bond in here, and alkynes have a triple bond. So if we look at this and we see all single bonds, we know it has to be an alkane. But the other way is to test using the formula. So if we look at the reference table here, remember our formula was C6H14 for our compound. And it says, here's the general formula for alkane. So we can just plug in and see, does this work? So if our N here is 6, 2N plus 2 would be 12 plus 2 would be 14. So this does fit with the alkane structural formula here. If we look, C6H14, does that fit in the alkenes general formula? Well, we have our 6 for our N, 2N would be 12, but we have 14 here, so that doesn't fit. And then same thing with our alkynes formula. Again, our N is 6, so this will require H10 here, but we have 14, so neither of those really fit with the structural formula that we have. So we can verify two ways that this is an alkane. We can use the general formula here, or we can use the structural formula and just do it by visual inspection. So we look and we see, okay, this has only single bonds here, and then we can test using the formula as well, and so we know this has to be an alkane. Alright, and what is the empirical formula for isomer 1? So we know the molecular formula for these isomers are C6H14. So to get the empirical formula from the molecular formula, we just want to reduce it as much as possible. See, what is the biggest number we can divide into both of these terms here? So the highest common factor here would be 2. So if we divide both of these by 2, we go from C6 to C3, and then H14 to H7. So we reduce this by, again, looking for what's the highest common denominator between these two subscripts, 6 and 14. The highest thing we could divide by here was 2, so that's going to leave us with C3H7. And 65 asks us, in terms of intermolecular forces, why is the boiling point lower for number 2, for isomer number 2 here, than for isomer number 1? So boiling point really comes down to intermolecular forces. So if we look at the two of these, what type of intermolecular forces are they both going to have? Well, they're both nonpolar. They're these big organic nonpolar molecules. So these are both going to have London dispersion forces, or van der Waals forces. So the difference between van der Waals forces between two molecules, you're really just looking at the size. So if we look at this one here, you're really looking for the longest chain. So here we have a chain of 1, 2, 3, 4, 5, and 6 carbons. That's one straight chain of 6 carbons. Where if we look at this molecule down here, the longest chain we can make, if we start over here, 1, 2, 3, and then take your pick which way you go, the longest chain you can make is 4. So because this first isomer has a longest chain than the bottom isomer, it's going to be considered a bigger molecule in terms of van der Waals or London dispersion forces. So the longer chain you have, the bigger the molecule is considered in terms of van der Waals or London dispersion forces. So the longer chain you have, the stronger those van der Waals forces are going to be, because the bigger the molecule, the stronger the van der Waals forces will be. So here we have a bigger, longest chain. That's why we have a higher boiling point for this one. So if you want to say, reframe this in terms of question 65, it says, why does isomer 2 have a lower boiling point? That's because it has a shorter, longest chain of carbon atoms, and would therefore be a smaller molecule and have lower van der Waals or London dispersion forces. So those lower intermolecular forces would give it a lower boiling point. Alright, thanks for watching this series of videos on the June 2013 Chemistry Regents, and I'll see you in the next video.